and that gives me the double integral. Okay, sorry, that's not a very good sentence, but whatever. So, okay, so that's the definition. Of course, we'll have to see how to compute it. We don't actually compute it. You know, when you compute an integral in single variable calculus, you don't do that. You don't cut into little pieces and sum the pieces together. Actually, you've learned how to integrate functions using various formulas. And similarly here, we'll learn how to actually compute these things without doing that cutting into small pieces. But, okay, any questions first about the concept or what the definition is? Yes? Well, so we'll have to learn which tricks work and how exactly. But so what we'll do actually is we'll reduce the calculation of a double integral to 2 calculations of single integrals. And so for these, certainly all the tricks you've learned in single variable calculus will come in handy. Okay, so yes, that's a strong signal, by the way, that if you've forgotten everything about single variable calculus, now might be a good time to actually brush up on, you know, integrals. You know, the usual integrals and the usual substitution tricks and easy trig in particular. This will be very useful. Okay, so yes, so how do we compute these things? That's what we have to come up with. And, well, you know, going back to what we did with derivatives, to understand variations of functions and derivatives, what we did was really we took slices parallel to an axis or another one. So, in fact, here the key is also the same. So what we're going to do is instead of cutting into a lot of small boxes like that and summing completely at random, we'll actually somehow scan through our region by parallel planes. Okay, so let me put up actually a slightly different picture up here. So what I'm going to do is I'm going to take planes, say in this picture, parallel to the YZ plane. I'll take a moving plane that scans from the back to the front or from the front to the back. So that means, you know, I set a value of x, and I look at the slice x equals x0, and then I will do that for all values of x0. So now in each slice, well, I get what looks a lot like a single variable integral. Okay, and that integral will tell me what is the area in this, well, I guess it was supposed to be green, but it all comes as black. So let's say the black shaded slice. And then when I add all of these areas together as the value of x changes, I will get the volume. Okay, let me try to explain that again. So to compute this integral, what we do is actually we take slices. So let's call S of x the area of a slice through, well, by a plane parallel to the YZ plane. Okay, so on the picture, S of x is just the area of this thing in the vertical wall. Now, if you sum all of these, well, let's see, why does that work? So if you take the region between 2 parallel slices that are very close to each other, what's the volume between these two things? Well, it's essentially S of x times the thickness of this very thin slice, and the thickness would be delta x or dx if you take a limit with more and more slices. Okay, so then the volume will be the integral of S of x dx. From, well, what would be the range for x? Well, we would have to start at the very lowest value of x that ever happens in our region, and we'd have to go all the way to the very largest value of x, okay? From the very far back to the very far front. So on this picture, we'd probably start, you know, over here at the back, and we'd end over here at the front. So let me just say from the minimum x to the maximum x. And now, how do we find s of x? Well, s of x will be actually, again, an integral. But now it's an integral over the variable y, because when we look at this slice, what changes from left to right is y. So, well, let me actually write that down. For a given x, the area S of x you can compute as an integral of f of xy dy. Okay, where now x is a constant and y will be the variable of integration. What's the range for y? Well, it's from the leftmost point here to the rightmost point here on the given slice. So there's a big catch here. That's a very important thing to remember. What is the range of integration? The range of integration for y depends actually on x. See, if I take this slice that's pictured on that diagram, then the range for y goes all the way from the very left to the very right. But if I take a slice that's, say, near the very front, then in fact, only a very small segment of it will be in my region. So the range of values for y will be much less. Let me actually draw a 2D picture for that. So remember, we fix x and we so we fix a value of x. Okay? And for a given value of x, what we'll do is we'll slice our graph by this plane parallel to the YZ plane. So now imagine the graph is sitting above that. And that's the region R. I have the region R, and I have the graph of a function above this region R. And I'm trying to find the area between this segment and the graph above it in this vertical plane. Well, to do that, I have to integrate from y going from here to here. Right? I want the area of a piece that sits above this red segment. And so in particular, the endpoints, the extreme values for y, depend on x. Because see, if I slice here instead, well, my bounds for y will be smaller.